is maintained within recommended limits. And this gives you an idea of what those thermal conditions are. Now, once you're outside of this thermal condition, if you're too cold, then you have something called hypothermic conditions. And if you get too hot, you go into hypothermia. Now, for the presentation here, we are going to be focusing on getting too hot. Now, one definition that we would like to start out with is heat stress, which represents a heat load that tends to increase body storage and elevate core body temperature. Now, if this body temperature is above 40 degrees for prolonged periods, what we realize is that you will get heat stroke, exhaustion, and in some cases, eventually die. Now, how can we prevent this? We first again come down to thermal comfort. Now, according to Ashray, thermal comfort is that condition of mind that expresses satisfaction in one's thermal environment. Now, there are several factors that contribute to one's thermal comfort. And when we look here, we have environmental and personal as main categories. Now, on the environmental, we have air temperature, humidity, airflow rate, and radiant heat. Now, because this thermal comfort is an individual thing, that person's metabolic rate and the level of clothing that they have will also determine their thermal comfort. Now, how do we achieve thermal comfort? We achieve it by finding an optimization of these 6 parameters, and these are normally represented on our bioclimatic charts, as shown here. Now, these charts vary based on country. So Africa versus Brazil will have a different thermal bioclimatic chart, but it won't vary that much. Now, there are other type of bioclimatic graphs that are shown here. Now, what is key from this chart is that as relative humidity increases, there's a reduction in the need of air temperature to achieve thermal comfort. For this presentation, we'll be sticking with the simpler bioclimatic chart and applying it to Jamaica to see if we fall into that thermal comfort zone naturally. Now, taking Jamaica's historical relative humidity, we are seeing that relative humidity normally lies between 77% and 78%. Now, when we apply that to this bioclimatic chart, we are seeing that we are outside of that comfortable zone, but we are in that acceptable zone. Now, if we take temperatures between 1991 to 2020 and use the average values, starting with the minimum temperature, we are seeing that we are still in that acceptable region. However, as you apply that mean temperature, that max temperature, we have drifted far away from that comfortable zone. Now, what does that mean for us? So our first problem is that our climate demands cooling. Giving you an example of why our climate demands cooling and how climate change has already impacted us. In 2023, it was a very hot year, and there were warnings given out about the impact of heat stress. And these are just some examples of heat stress being a main highlight in the news media. And it was quite interesting to see that for Puerto Rico, there was a warning: walking after 10 a.m. is not recommended. That's how hot it's getting. Now, heat stress affects everyone because it's an invisible killer. You don't know your heat stress until maybe sometime it's too late. And even our food security is being threatened by heat stress. So what we can conclude, to summarize, is that cooling has become a necessity for survival because of rising temperature in the Caribbean. Again, our climate demands cooling. Our second problem is our buildings are not designed for optimal thermal performance. Take example here, a tropical climate would normally require low thermal mass materials, and these materials allow for heating up quickly and cooling down fastly. And therefore, you have this cooling heat, it's hot in the day, but at nighttime it's a little cooler. However, we are building our buildings mostly with high thermal mass materials such as concrete. And we are doing this because we are trying to prevent these type of scenarios after hurricane has passed through the island. And therefore, we find ourselves building our buildings for one aspect of our climate and not about the thermal comfort. And therefore, we are having challenges in maintaining cooling in our buildings. And therefore, this project, Making Buildings Cool Again, is looking at how can we in the Caribbean find ways at alternative solutions to cooling. Now, these are the overarching objectives, question, and expected outcome for the project. However, I'm going to just ask, one of the questions is, will active cooling become essential or stay optional in future climates? And for this presentation, we are going to just focus on phase change material, which a previous speaker had laid the foundation for. Now, for phase change material, this is a material that absorbs heat or releases heat and maintains that same temperature while it's transitioning its phase. And typically, as you've seen here, that solid material is changing from liquid to solid at room temperature. And these are the type of materials that we need. Now, there are several types of these materials that exist. However, we are only interested in those that is within that thermal comfort zone that we mentioned before. We then took, so these materials will work in a building cooling setting as follows. So in the day, you have that solid material and it's frozen and it's absorbing the heat from the building to try to keep the temperature cool. Now, once it absorbs that heat, is eventually going to turn into liquid. And then you now need a material that is going to take this liquid phase change material and freeze it. Now, we can use our nighttime conditions to do this freezing, or we can use maybe an air conditioning system depending on our electricity rates. Some results from the experiment. So currently we have a pending publication that explored the potential of Jamaica's hot and humid climate to solidify the phase change material during the night. And we tested a 24-degree phase change melting temperature material. Now, once we got the results from that field experiment, we took that information and applied it to 25 weather stations across Jamaica to see where would this material be ideal to operate. Now, we created this map, and what we realized in our experiment is that our interior areas were able to solidify this material for 70% of the year. And this was quite interesting because of the elevation of this area. However, our coastal regions, we realized that they are low thermal potential, and therefore they might need more of a higher phase change temperature material to be able to utilize this technology. Now, in conclusion, our climate demands cooling. Our building materials are not optimized for thermal performance based on our climate. Phase change material is a promising technology for cooling buildings in Jamaica. However, some food for thought. An air conditioning system is designed to create a temperature of about 11 to 15 degrees Celsius between inside and outside temperature. Our AC system may not be the solution in a warmer climate with poorly designed buildings. We need to rethink how we construct buildings. This may involve having a climate-resilient building code tailored to each parish. And finally, we need to model how phase change material behave under future climate conditions to ensure we select the right phase change temperature. Those are my references, and thank you for listening.
Great, thank you, Donnelly. Perfect, on time too, well rehearsed, and I thought those were interesting results. An interesting approach to what is a clearly a need now. So I know between Dr. Chadee and Dr. Felix, we'll get some good questions. Now I want to go straight into the last speaker in this session. That is Miss Shamika Spencer. Very familiar. Shamika is actually my PhD student. Shamika is an Antiguan and Barbudan PhD student in environmental studies at the UWI Cave Hill campus. Her research focuses on optimizing the ratios of sargassum and seaweed with other substrates like rum distillery wastewater to enhance biogas outputs. She completed her undergraduate degree in biology and earned an MSc in biosafety, both at UWI Cave Hill, and has a lifelong passion for environmental sustainability, and wants to continue to innovate. All right, so the topic of Shamika's talk, I'm not seeing Shamika. Are y'all seeing Shamika? Yeah, I see her now. All right, so the topic of Shamika's talk is biomethane production from sargassum seaweed and rum distillery waste, a sustainable fuel solution. All right, so I'm gonna ask Shamika to share screen and unmute. Go ahead, Shamika.
Are you seeing my screen now?
Yep, I see your screen share.
Okay, thank you. Okay, good morning, everybody. I'm Shamika Spencer, and I'll be presenting on biomethane production from sargassum seaweed and rum distillery waste. So about my presentation, I'll go into some background first, then I'll get into my literature review. I'll go into the problem, and then I'll speak about the research methods, and then I'll conclude my presentation. So for a little bit of the background, so biogas is a very flexible source of renewable energy. And this is mainly because of the fact that methane, it can replace fossil fuels in different uses, such as generating electricity, powering vehicles, and also producing heat. And we know that fossil fuels emit harmful gases into the atmosphere, which currently they are contributing to global warming events. And methane is a byproduct of anaerobic digestion, and it is a very energy-dense fuel with efficient storage capacities, and it's becoming very popular and highly sought after. So I'll get now a bit into my literature review. So sargassum, it migrates to the Caribbean from the Sargasso Sea, and the Sargasso Sea is in Africa. And currently the most popular species or most abundant species that we have in the Caribbean are sargassum fluitans and natans, and they are accumulating along our coastlines. When sargassum decomposes, it produces cytotoxic gases, such as hydrogen sulfide and ammonia gases. And these can cause different effects on different bodily systems, such as nervous, cardiovascular, respiratory, and reproductive systems. And there was previous research conducted in the Renewable Energy Lab here at the UWI Cave Hill campus, and it shows that sargassum seaweed can successfully produce biomethane through the anaerobic digestion process. It's important to note, though, that the ideal carbon to nitrogen ratio range for anaerobic digestion is 20 to 30, but sargassum's carbon to nitrogen ratio falls a bit short of that at 14, which is relatively low. So what is anaerobic digestion? This is the breakdown of organic materials in the absence of oxygen to produce methane and carbon dioxide as the end products. And there are four main stages of the anaerobic digestion process, to include hydrolysis, acidogenesis, acetogenesis, and methanogenesis. And there are certain key factors that influence the optimization of the anaerobic digestion process, such as pH,